the mean value theorem. We are going to be interested in the second one, but it's nice to know the first one. Okay, so what is going to be the first one? What is going to be a rules theorem? Okay, rules theorem. This theorem is mostly used in algebra, and in calculus, it's going to be a foundation of a second one that we're going to be interested in. Let me just look at the theorems. You can get this one. It's a natural type of natural results that you're going to have. You see, suppose you'll be given this nice function. Nice to get the geometry of the problem first. You see, this is going to be the one. And we are going to have a, so we're going to have a function. Look at this function. This is the graph of your function. So this point is A, this point is B. Now look at the condition that this function would have. As you can see, this function is continuous. It's continuous on a closed interval of A and B because there is no gap, no holes. And this function is differentiable. It's differentiable because the graph has no sharp corner. So it is continuous and it's differentiable. Something else that's important for this graph is the intercepts. You see, the intercept of this graph is going to be A and B. So the y coordinate is 0. So f of A and f of B happen to be equal to the 0. Okay, so this function would have 3 conditions. I write it down the condition for you. You see, the one that are going to be interested is going to be a little bit better. So the condition of, sorry, the condition of this theorem are going to, this graph, if you like, is going to be that f is continuous. We call it first condition on the closed interval of A and B. You can see it, there is no gap. Second part, there is no sharp corner, so f is differentiable. F is going to be differentiable. We take a differentiability on open interval of A and B. We already talked about it open because if you want to consider that A and B, then you have to consider one-sided derivative. So we ignore it. But if it's happened to be differentiable on a closed interval, that's fine with us. Okay, but the third condition is, you see the third condition? The third condition is the intercept of the graph. F of A and F of B are going to be equal to the 0 because this is the intersection of the x-axis and the graph. Okay, so this is 3 conditions that you have. Now this is calculus. You see what's going to be the conclusion over here. Remember, we were interested in maximum and the minimum so far. And we talk about the relationship between, see, this is, you get a maximum here. And we already talked about it. At the maximum point, remember, this is it, you get a maximum here. So now you get a tangent line. So what type of tangent line are you going to have? Since the point is maximum, so this tangent line must be horizontal. So there is going to be a point that you're going to get a maximum. You see, there is a point that you get this maximum. What is this point? So this point is going to be a point like C. So there is a, because the function is continuous on a closed interval. Remember, according to the theorem that we talked about it already, so there must be a maximum. So there is a C such that at C, the graph would have, the function would have a maximum. At this maximum, the tangent line would be horizontal. And we know that when the tangent line is horizontal, the slope is 0. The slope is derivative. So f prime of C is equal to the 0. That's it. That's a rules theorem. So what's a rules theorem? Rules theorem tell you that if these 3 conditions satisfy, okay, then there is a number. There is at least one number. You may have more. At least one number. C inside It cannot be at the boundaries, if you like, with this condition that we have, because we talk about the derivative, and the derivative is only exists inside the interval. So there is at least one number C inside A and B such that f prime of C is equal to the 0. That's it. That's a Rolle's theorem. Something obvious. Your graph may go up and down. You see, if you get this graph, for example, if you get this graph, you are going to get more points. You see, at this point, you get that maximum, that you get the minimum. And in all of these, you get lots of these C's, okay? For example, you may get a C1 over here, C2 over here, C3, C4. So because of the maximum and the minimum that's happened, and the continuity would guarantee that. And this condition at the end would guarantee that C cannot be f of A and cannot be f of B, because we imposed the condition that this would be 0. So there is a C in this interval that you get a maximum or you get a minimum. Okay, that C cannot be this one, cannot be at A or B. Otherwise, your function must be f of x equal to 0 all the time. Okay, so this condition, we are going to use it to make sure that the C is inside the interval. And if it's going to be inside the interval, then we can use the Fermat theorem. Remember, you get a maximum. C is in fact a critical number. It's going to be a critical number's differentiability, so you get f prime of C equal to 0. That's it. That's the Rolle's theorem. So from geometry point of view, as usual, you get these horizontal tangent lines, so it's not bad to emphasize. So from geometry, okay, geometrically by the Rolle's theorem, okay, by the Rolle's theorem, there is a horizontal tangent line. There is a number. There is a number C inside, okay, inside A and B, such that inside A and B, such that the tangent line, okay, tangent line to the graph, okay, tangent line to the graph of the function y equal to the f of x, okay, at C, at x equal to the C is horizontal. You see, that is going to be the terms of this great theorem. Any question? So, and the proof is easy. In algebra, they love this one. Why they like it in algebra? You see, that in algebra, you would like to solve equations. So from the algebra point of view, for example, this is going to be the case that you see if you have this equation, f of x equal to 0 for your function, when you say f of A is 0, f of B is 0, this means A and B are solution of this equation. So this condition all will tell you that if, you see, from algebra point of view, if f of x equal to 0 has two solutions, A and B, then you see when say f prime of C equal to 0, this means if you differentiate this equation, that equation is guaranteed that you get at least one solution. So f of x has two solutions, the A and B, then the equation, you see the equation f prime of x equal to 0 has at least one solution. Okay, one solution between A and B. It's the way they use it in algebra or from the algebraic point of view. So between any two solutions of the given equation, if you differentiate the equation, that equation would have one solution less. So this means if this equation would have three solutions, then you differentiate it, the result would have at least two solutions. If this equation would have 10 solutions, if you differentiate it, that equation would have at least 9 solutions. We can use this one to prove a great theorem. We call it fundamental theorem of algebra. And that's the case that if you have a polynomial, equation, that polynomial equation would have always n solution. Okay, of course, some of the solution can be complex, but we can use the rules theorem to prove it. So these are the type of ideas that we can use in algebra to get this result. Now, the way I'm going to use it, this is the way it's happened in your book. The way I'm going to motivate this one for that great theorem, mean value theorem, which is our concern. What I'm going to do, I'm going to consider, you see, if you push this a little bit up, you see, look at this one. So if you push it a little bit up, what is going to be your graph? Look at this graph. This is again the graph. If you have this one, oh, I'm sorry, I made a mistake here. I should have, this is the original one. This is the original one. I'm going to push it up. You see, I push it up. If I push it up here, you see what's going to be the difference. This is the A and this is the B. So my graph, the third condition would be that this is A, this is B. So the third condition here is f of A equal to the f of B equal to the 0. The third condition here is only f of A equal to the f of B. Okay, so you can have the rules theorem with the third condition, the fact that as soon as f of A is equal to f of B, that would be enough. So you don't have to worry about to make it equal to the 0. Okay, because I'm going to use this version for the mean value theorem. So I'm going to write this one officially as a rules theorem. Then I extend it quickly to the mean value theorem. Any question? So you see the result of this. Okay, so let's, for the last time, just see what is the rules theorem. If you're going to be a math major, of course, you are going to see it. The proof is as I told you. So I'm not going to write the proof of this one, but I told about how to do it. But I write the mean value theorem for you. So officially, this is the rules theorem that we are going to use. We are not going to question you directly on this, but I give you an example, and there are some problems in your book. You can pick one of them. Suppose a function f is defined, okay, defined on the closed interval of A and B, such that the following conditions satisfy. The first one, continuity. F is continuous. F is continuous on the closed interval. That is the first condition. Second condition, F is differentiable. F is differentiable on the open interval. I talk about the reason. You see, the reason is you can have it at the closed interval, but then you have to talk about differentiability at A and B. The third condition, simply as we simplify it, f of A equal to the f of B. In your book, they say f of A equal to the f of B equal to the 0, but you don't need it. If there is three conditions satisfied, then there is going to be horizontal tangent line. Okay, then the conclusion, then there is a number, at least one number, okay, a number C inside this interval such that f prime of C is equal to the 0. Basically, this means, as we talked about it, this equation will have one solution, or you are going to have horizontal tangent line. Okay, any question? Let's give you one example to see how we're going to check it for a problem in your book. And of course, would be useful for you when we get to the mean value theorem. We just simply give you one equation, one function, and they ask you to check this condition. That's it. Okay, determine, check. Determine whether, okay, whether Rolle's theorem. It's a French mathematician. You can search it on the internet if you want to know about the theorem and the history. Determine whether Rolle's theorem can be applied. Can be applied to the function. To the function. The function is f of x. F of x equal to x cubed minus 2x squared minus 4x plus 2 on the interval of a -2 and 2. Okay, you check the condition to see it's satisfied. They usually say, if so, give us the C. So if your answer is positive, find all values of C. So you realize that what they are talking about. You see, that's the problem on the Rolle's theorem. And it's very similar to the mean value theorem, but the way you're going to write it down is you must give us all the details, otherwise you lose point. 1, 2, 3 conditions. So you have to check that these 3 conditions are satisfying. Are you ready? Solution. Check. Condition 1, continuity. What type of function is this one?
Polynomial.
Polynomials. And you know that polynomials are continuous forever. But you want it to be continuous on this interval. Done. So you explain that f is a polynomial. Polynomial or a polynomial function. And is continuous. It's continuous everywhere. And just focus on the condition of the theorem. Continuous on the closed interval of -2 and 2. Done. Remember, on the test, you have to write it down. It's similar to the condition of the mean value theorem that we're going to see in a minute. Okay, that's first one, it's done. Second condition, differentiability. Differentiated. Easy function to differentiate. Mostly it's going to be polynomial, nothing else. So f prime of x is going to be equal to 3x squared minus 4x minus 4. That's it, highlighted because you're going to use it. If you can find the derivative of this function or any function, this means the function is differentiable. It's differentiable everywhere, but you want it inside this interval. So we just write it down inside. Okay, this is it. And you can say that, you know, I have the derivative for you. So this means, and so f is differentiable. F is differentiable. It's differentiable everywhere. But remember, you want it on open interval, -2 and 2. Second condition is also satisfied. If you cannot find the derivative of this function, okay, or it's going to be the point inside which is not going to be differentiable, then you can't do it. Okay, any question? Third condition. Find f of 2 and f of -2. Show that they are equal to each other. Third condition. Find f of -2 into the function. So substitute. That gives you -2 cubed minus 2 times the -2 squared minus 4 times -2 plus 2. Check this one. Negative 2 cube would be negative 8. Negative 8, and this is going to be 4. Again, negative 8. And this would be positive 8 and 2. Okay, these two would cancel out. Negative 8 plus 2 would be 6. So f of negative 3 is 6. You see, this is why I just give you those extra extended condition for number 3. So that's f of negative 2. Find f of 2. Remember, you don't have to have 0 here. You know, it just, the numbers must be equal to. If you get a 0, that's a bonus. So f of 2, same thing, substitute. That give you 2 cubed minus 2 times 2 squared minus 4 times 2 plus 2. Check this one. 2 cubed would be positive 8 this time. Positive 8. This is going to be 4 minus 8 plus 2. Again, these two would cancel out. And that give you negative 6. Did I miss anything? Yeah, I missed the negative here. Let me just check this one. These two would cancel out. I have negative 8 plus 2, so that would be negative 6. Okay, and this would be the same thing, negative 6. Okay, negative 6, both of them. That's it. So we have the fact that f of negative 2 is equal to the f of 2. So all the conditions satisfy. 1, 2, 3. Any question? So you have to write it down. If any of this condition is not satisfying, you stop. You're not going to continue, okay? So you have to be worried about the third one in your book, okay? And you know, the other two as well, but I give you one in the case of the mean value theorem. So this means we can have the conclusions. The conclusion is, so you say that yes, Rolle's theorem can be applied. Rolle's theorem can be applied. Now we know what does it mean. It means can be applied to find a C, okay? To find a number C, it's just for information, number C inside the negative 2 and 2, such that you can solve that equation right away, we don't mind, such that f prime of C is equal to the 0. So you have to solve this equation. F prime of C, what's f prime of C? It's f prime of X. We change the X into the C, we solve the equation. Okay, some people, they stay with the X and they solve for X, which is going to be the same thing. So bring f prime of C. So I remind you that f prime of C in this problem is going to be 3c squared minus 4c minus 4. So you get this one equal to the 0. Sometimes you can factor it, but sometimes you may need quadratic formula. So intentionally, I'm going to use quadratic formula for this one because it cannot be factored. Okay, so be prepared for it. You may need this one. So that's it, quadratic formula. C equal to, remember quadratic formula, negative b, negative 4, plus or minus b squared. That's going to be negative 4 squared minus 4 times AC. You multiply these numbers, 3 times the negative 4. Divide by 2 times A, 2 times 3. That's quadratic formula. Remember, I gave you this one the other day. Just repeat it again. X equal to the negative b plus or minus the square root of a b squared minus 4ac divided by 2a. You need this one, even you need it for the mean value theorem. Okay, go on, simplify it. So that gives you a 4 plus or minus the square root of, that's a 16. And negative would be positive. 4 times 4, 16. 16 times 3, 48 divided by 6. So that gives you 4 plus or minus, okay, square root of 64 divided by 6. So 64 would be 8. Again, we can factor it if you want. So this is going to be equal to, just continue. The top is going to be what? 4 plus or minus 8 divided by 6. So I'm going to have two solutions. So if I go with the positive one, I put it here. So that gives me 4 plus 8 over 6. So 4 and 8 would be 12. 12 over 6 would be 2, one solution. So if I go with the negative 4 minus 8 over 6, okay, and that gives me negative 2/3. So I have two solutions. C equal to there. Okay, C is equal to 2, one solution, and C is equal to the negative 2/3. You just check to make sure that both of them are inside this interval. Okay, so since we would like it to be inside the interval, so the interval is -2 and 2. So we are not going to collect a C equal to 2. It's okay, you can have the C equal to 2 as well. But since we emphasize that there is a C inside the interval in general, inside the interval, the only solution is going to be C equal to the -2/3. Okay, it's fine to write both of them even because it's a polynomial type, but in general, the number must be inside. So I write it down over here for you that you just check it. C equal to -t is inside. Inside -2 and 2. So you pick this one as one solution. One solution is guaranteed. If you get more than one, you have to test it. You have to check to make sure that this is going to be part of your solutions. Great theorem. Any question? But sometimes when it's a face-to-face, we focus on this theorem too. But this is just a preview really for the big one that we are interested in. So I just give you the result because this example, because it's very similar to what we are going to do later. But we are not going to be directly focusing on this one. We go to the main one right away. So I'm going to explain you the main one. Any question? So get to know it. It's nice to investigate, to test. You will see the theorem, the mean value theorem in a minute, which is the same thing. So it's not bad to see how you discipline yourself to check a great theorem. Any question? Now let's go to the big one. The big one is an extension of this theorem in calculus that we love it. So what is going to be the big one? Come back here. Look at this theorem once more. So what do we have? Let's focus on this. Let's just repeat it over here. So this is going to be the theorem that we are going to be interested in. Anything you want to do in calculus from now on up to the end of calculus 3, you are going to be using this theorem. Such an important theorem. Okay, we give you one question on this on the next test, and we repeat it on the final. Okay, because we want to make sure that when you take calculus 2 or in future, you remember this great theorem, mean value theorem. So nothing from the rules on the test. Mean value theorem. Mean value theorem. We abbreviate it as MVT from now on, MVT. You see, the situation of the mean value theorem is that we are going to be given a function like the one you did for the rules theorem. This graph is nicely, we are going to we change the third condition of the rules theorem. Remember, the first condition is differentiability. The second condition, the first condition is continuity, second function differentiability. The third one was f of a equal to the f of b. I'm going to change the third condition. Let's see what's going to be the graph this time. You see, that's the one. If you consider your graph to be this form this time, okay? So suppose this is going to be your graph. So again, this is going to be A, and this is going to be B. Okay. So what is the situation now they have? Of course, this function, as you can see, is continuous. So the first condition is the same because there's no gap. This function is differentiable because there is no sharp corner. But the difference is these two, you see. We just move it, there's going to be a deviation, if you like, if you consider it with the other one. So the change is going to be, you see, this is your f of a, and this is your f of b. So the third condition has been changed. Okay, f of a is not equal to the f of b. Now let's see what would happen to the theorem. Remember the point C that we got it at the maximum. It's the same thing over here. We can find a C. So there is a C. You see, it's going to be almost here. So, I mean, the C is here. And this would be the maximum value of the function, if you like. And there is a tangent line. You see, there is a tangent. Of course, it's not going to be horizontal. So what's going to be that tangent line? You see, this is going to be that tangent line that we talk about it. Okay, so this is going to be a tangent line that we talk about it. But this time, this tangent line is not horizontal. When the tangent line was horizontal, it was parallel to the x-axis. But it's mathematics. You see, in mathematics, we never give up. So we'd like to find out what will happen really to that idea that we focus on the other part. So we say, oh, okay, I can find another line to be parallel. Let's look at this one. If I connect these 2 points together, you see, nice. I got the line. So I got the line that passes through these 2 points. You see these points? So I'm going to call these points over here A, and this point over here, call it B. So what I have the fact that in this type, if even I don't have the third condition of the Rolle's theorem, so I do have the first two, the function is continuous because there is no gap. The function is differentiable because there is no sharp corner, but I don't have the third condition. But I can have something similar to what I did over there. So in this case, there is going to be a C such that the tangent line to the graph of the function at C, which is going to be T, is going to be parallel. It's going to be parallel to the line connecting the point A to the point B. Okay, now what is A and B? So I know that the A is going to be what? The coordinate of the A is going to be A comma F of A. And the coordinate of the B would be, okay, the coordinate of the B would be B F of B. You see, that's the situation that we have. Any question? Now, let's see what you know about this. When the lines are going to be parallel, you know that what's going to be a relationship between the slope. Any suggestion? When two lines are parallel, what do you know about the slope?
The slope is the same.
Excellent, same. So the slope of a tangent line must be equal to the slope of the, we call it secant line. See, that's one. But we know that the slope of a tangent line, this is calculus. The slope of a tangent line is derivative of the function. So the slope of this, okay, the slope of the tangent line is f prime of c. And the slope of a line, you know that the slope of a line passing through 2 points can be found by using the formula of what? y2 minus y1 over x2 minus x1. Rise run. So this is going to be what? F of b minus f of a over b minus a. That's it. So instead of having f prime of c equal to 0, you can expect this equation if you like. So there is a c between a and the b that satisfies this condition. If you think about it, you see f prime of c is going to be kind of rate of change. F of b minus f of a over b minus a is like the, okay, it's like the average value of the function. So this means you are going to get the average value of the function at the point if you like. And this connection together is going to be called mean value theorem. Some people love this one, but we love to cross multiply it. So we can use both versions. This version is to define, or when we prove theorems, we use this version, cross multiply it. If you cross multiply it, you are going to get this version, f of b minus f of a equal to the f prime of c times b minus c. Such a great theorem. You see, this equation that you get over here, we call it the mean value equation. So we extend, you say if you have the rules theorem, in the case of the rules theorem, remember these two happen to be equal to each other. If they happen to be equal to each other, that would be zero. And you know that a fraction, if the numerator of a fraction is zero, the result would be zero. So we get f prime of c equal to zero. So that's why some people, they say, oh, you don't need the rules theorem, you know. It's the mean value theorem is going to be more general one. So I'm going to write it down for you. You know, when I was in high school, they give us this as a proof, of course, but this is not a proof. Okay, this is just indication of the proof. This is the way we do in mathematics. And we try to find something, but when we find that, then we get serious and prove it. It's a great theorem. I give you a short proof because this is the crunch of calculus. Such an important theorem, we call it midwife of calculus. You know that the midwife job is to deliver, because this theorem by itself is just a theorem, but it delivers number of the great theorems in calculus. From now on in this course, anything you want to do, you have to go to the mean value theorem. That's why, you know, we like this theorem. And it's a secret that if you want to prove a great theorem in calculus or in differential equation, all those great theorems, you have to go through the mean value theorem. That's a secret of this, you know, of these great theorems. Okay, so let's make it official. What is going to be mean value theorem? Okay, any question? Go get to know it. It's a great theorem. And there are a group of mathematicians. They are very jealous about the mean value theorem. So what they do, those results that you're going to see in calculus, and I'm going to give you one of them today. What they do, they say, oh, you don't need the mean value theorem to prove those results. They prove all the other results, application of mean value theorem, without using the mean value theorem. Okay, and they claim that, you know, we should do the same thing. But the difficulty is that the theorems that they use are the one that, you know, you have to know a little bit more in mathematics. It's got to be a math major, for example. And if you get to the, you know, your fourth year graduate course, then you can understand those theorems. Okay, so that we keep it. Their works are nice, but the order of, you know, for a study, we prefer to be a traditional one, and this is going to be the case. So if you search on internet, you see quite a lot. You know, it's a great theorem, so everybody can say something about it. There you are. This is what we are going to talk about it. What is mean value theorem? Make sure you know the statement of the theorems, and you need it for calculus 2 as well, and calculus 3. So there you are. What's the statement of the theorem officially? If f is a function, f is the extension of the rules. If f is a function that is defined, again on a closed interval, very much like the rules, satisfying only two conditions, such that conditions, the first and the second only. The first one that you have to investigate for us, f is continuous. F is continuous on the closed interval of a comma b. Second condition, I write them together, differentiable. F is differentiable. Differentiable on open interval. Again, if it's happened to be closed, that's fine. Okay, there is no third condition. So if these two conditions satisfy, then there is a C again. There is a horizontal. There is a tangent line, but it's not going to be horizontal. Then there is, again, at least, you may get more. At least one number, a number. Okay, a number C inside A and B, such that you get a mean value equation. F prime of C is equal to F of B minus F of A divided by B minus A. That's one version, or the other version is cross multiply. You can use either one, but for this section, this is easier. F of B minus F of A is equal to the F prime of C times B minus A. You see that is going to be the mean value theorem. So as soon as you check the first and the second condition, you have to form this quotient. Okay, you form this quotient and you solve for C. And again, we talk about geometry. From geometry point of view means there is a C inside. Okay, again, if you want to make a record for yourself, geometry, that's the way you remember it. Okay, from geometry point of view, this means that there is a, if you have the condition, there is a number C inside A and B such that the tangent line to the graph, okay, the graph of y equal to the f of x at x equal to the C is horizontal. It's going to be horizontal to the line. Okay, to the line through these points. Through the points. Okay, point with the coordinate A comma f of A and B comma f of B. Okay, and this is going to be the case. That will help you to remember it, okay, for future, to see how we're going to do it.
Do you mean parallel or is it horizontal to the line through those points?
Oh, yes, thanks a lot. It's parallel, of course, yes, thank you. It's parallel, thank you. Very good, yeah, parallel. Parallel to the line through the points A, F of A and the B, F of B. Okay, so it's a great theorem, really. That's a piece of history of calculus. And there are different proofs. I give you a nice proof just for the record. You can keep it. We are not going to ask you to prove it, but it's a crunch of calculus. So it's not bad to see why we create that. Okay, why we create that rules theorem. This proof is maybe different from your proof, but it's a very standard proof. So what I'm going to do is I'm going to change this one to a function that satisfies a rules theorem. You see the function that I'm going to introduce is this one. Remember the reason that we got this one, because the curve was not, these two lines are not going to be parallel. So we move it a little bit, this is the deviation that you got. So what I'm going to do, I'm going to introduce a function for you. That function would be this difference, the difficulty that you have over here. You see, I'm going to pick a number x here. Then I'm going to consider the difference between the y values of the x from this tangent line. Okay, and from the graph. You see, this is the graph. So my function that we're going to introduce for you is going to be a difference between this is it, difference between the value of the function for the f of x or the value from the, you see this is going to be this portion over here is going to be f of x. Okay, and this portion over here, the green one, this is going to be the value of the, I'm sorry, all of them over here. You see this red one and all of them together here. This is going to be the, I call it y of AB. I'm going to consider the function is going to be difference between the, you see this is the y coordinate of the point from the line, which is y, minus the y coordinate from the graph, which is f of x. And I'll show that this function would satisfy the Roule's theorem, just for the record to see it, and to see how this great theorem is proved, but we are not going to ask you to prove it. So in just a few seconds you can prove it, and this is a piece of history. It's nice to have a proof. Again, this is one of the proof. So what I'm going to do is I'm going to introduce a function that satisfies the Roule's theorem. That's it. Define a function g on the closed interval of a and b. Okay, that's it. By the following. That's it. I define the g of x. As I talk about it, it's going to be difference between f of x, and I call it y of ab. Y of ab means equation of a tangent line. So what is going to be pair y of ab is the tangent line, is the equation of the tangent line. Okay, tangent line T that we talk about it. So equation of a tangent line is going to be, okay, sorry, y of AB is going to be the equation of the, not the tangent line, equation of the line, equation of the line through the point. Okay, the root point of the A with the coordinate of A and f of A, and the B is going to be P and f of B. You know that when two lines are given to you, can find the equation of the line by the formula of y minus y1. I write it down, y minus y1, y minus f of A equal to this slope, f of B minus f of A over B minus A times x minus A. Remember y minus y1 is like y minus y1 equal to the m times x minus x1. So I move the y to the other side. So that gives me y equal to the f of A plus f of B minus f of A over B minus A times x minus A. You see, take this one here. This is a function that satisfies the Roule's theorem, and then you can get your result. Just for the record, g of x is f of x minus f of A minus f of B minus f of A over B minus A times x minus A. You see, that's a g function. This function would satisfy the condition of the Roule's theorem. There is a C, G prime of C equal to 0, G prime of C equal to 0, give you the mean value theorem right away. Okay, so note that condition 1, G is continuous. G is continuous on a closed interval of A and B. And why? Because f is continuous. This is number. These are all numbers, x minus a. That's the first condition. Second, differentiability. G is differentiable. G is differentiable. I want to give you the condition of the Rolle's theorem. Differentiable on A and the B. And what is the derivative? G prime of x equal to, if the f of x would be f prime of x. If the f of a is a number, would be 0 minus. You see the derivative of this part is just 1. And this is just a number. So it's going to be minus f of b minus f of a over b minus a times a number. So g prime of x is f prime of x minus f of b minus f of a over b minus a. That's g prime. So the first and the second condition of the Rolle's theorem satisfy. I need the third one. What is g of a? Replace x by a. This would be f of a minus f of a, which is 0. This would be a minus a, which is 0. So g of a would be 0. Write down for you. F of a minus f of a minus f of b minus f of a over b minus a minus a. Everything would be 0. 0, 0. So that would be 0. So g of a would be 0. That's it. Similarly, g of b would be 0 too. So I have the condition of the Rolle's theorem. Similarly, g of b would be also 0. Because you put the b here, b minus a and b minus a would cancel out. And you have f of b minus a minus f of b minus a. So everything would be canceling out. So G satisfies the Rolle's theorem. So there is a C such that f prime of G prime of C equal to the 0. G prime of C equal to 0, that gives you the mean value equation. And then you prove it. This proof was done by Agustin Cauchy. You know, the mean value theorem is the work of Cauchy. So we call it Cauchy mean value theorem. Just wanted to see this piece of history. So G satisfy. So Rolle's theorem can be applied. Rolle's theorem, okay, can be applied. So this means there is C such that G prime of C equal to 0, and you substitute here, and that gives you the mean value theorem. Okay, I'll go to the next page to check it. So this means f prime of C minus f of B minus f of A over B minus A is equal to the 0 because of the G prime. Moving to the other side, you proved a great theorem in calculus. Again, just for your information. If you are a math major, you are going to prove everything in future. See, I wanted to see the connection, how we connect the rules. So without Rolle's theorem, you can't do it. That's why I state at least the Rolle's theorem, but I prove the mean value. There are different proof of this one because everybody wants to be famous. I try to give a proof of the mean value theorem, of course, but this is a very short one and a good one from Agustin Cauchy. Okay, any question? Now, your job is not to prove this one for us. Your job is to be able to apply it. So what we do, easy. We give you one function and one interval, and we ask you to do it. So you have to check the condition, form this one, cross multiply, find the C for us. Easy case. One question on the on your test now, and one on the final. So let's do it, and then we're done with the main value. Any question? So read it if you are interested in a little bit more detailed mathematics. Really, this is the case. Otherwise, you just use geometry just to get understand it. Okay, this theorem, because it's a great theorem. And in calculus, you will see from now on, everything I want to do, I just use the mean value theorem. So this is your job. Example. Check to see, determine. Okay, determine better. The mean value theorem. Mean value theorem. Or in exam, we may just say MVT. Determine if the MVT can be applied. Can be applied to the function. To the function. There you are. F of x equal to x cubed minus x squared minus 2x on the closed interval, okay, -1 and of course, if so, if your answer is positive, find all values of C. That's it. This is your job. Any question? Are you ready? Two conditions to check. Two conditions to check. The first one, continuity, of course, it's polynomial. It's continuous. Second condition, differentiability. Of course, differentiated. 3x squared minus 2x minus 2 is differentiable. So it can be used. Form this one. Cross multiply, find the C. That's it. Okay, solution. But you have to write the condition for us, otherwise you lose points on the test because you want to investigate. Okay, this is the way you're going to check. First condition, continuity, polynomial. You mentioned that f is a polynomial. F is a polynomial. And so is continuous. So is continuous. You just say continuous, polynomial, continuous, we accept it. But it's continuous everywhere, but you want it, remember, on a closed interval only. So that's your first condition. Okay, you have to mention it, even if you say f is continuous on closed interval -1 and 1. Be satisfied. And you did check the condition. Question? Second condition, differentiated. F prime of x is equal to 3x squared minus 2x minus 2. Carefully differentiated, because that would be important when you go on. So it's differentiable. And so f is differentiable. Again, it's differentiable everywhere, but you want it only on open interval, -1, 1, done. Although it's differentiable everywhere, but you just stay with the condition of the theorem. Remember, there is no third condition, just the first and the second. Okay, then we say, oh, MVT can be applied. MVT can be applied. Okay, can be applied to find the C. to find a number C. Number C, okay, you can do it right away. I just explain it. Inside -1 and 1, such that, okay, such that mean value equation, f prime of C equal to, remember, f of B minus f of A. B is the bigger number, A is the smaller number. F of B minus f of A could be f of 1 minus f of -1. Divide by B minus A, 1 minus, make sure don't miss the negative sign, minus -1. Okay, this is A, this is B. Now stay to the right and simplify the bottom. So that give you f of 1 minus f of -1. Okay, divided by 1 and 1. Over here would be 1 plus 1. So this is your equation, f prime of C equal to f of 1 minus f of -1 divided by 2. So your job is bring f of 1, bring f of -1, and f prime of C, and substitute in the equation and get the C done. Okay, so I remind myself what I have. F of 1, go to the function, find it, f of 1. F of 1, 1 minus 1 minus 2. 1 minus 1 minus 2. That gives you -2. That's f of 1. F of -1. F of -1. Go to the function. -1 cubed minus -1 squared minus 2 times -1 equal to -1 cubed would be -1. -1 squared would be +1, that give you -1. And 2 plus 2. You simplify that, give you 0. So f of -1, f of -1, f of -1 is 0. That's the second number question. F prime of C, you just change the x into the C. And some people, they don't change it. We don't mind if you do it, but I change it. F prime of C is equal to the 3C squared minus 2C minus 2. Okay, now bring everything in this equation and solve the result. F prime of C, 3C squared minus 2C minus 2 equal to f of 1, -2, minus f of -1, 0, divided by 2. So that gives -2 over 2, which is going to be -1. Okay, now you move this one to the other side and then decide how we're going to solve that equation. Okay, all the time you have to make it an as equation first. So add it. Okay, add it to this part to make the equation that you want to solve. So the result is going to be 3C squared minus 2C minus 2 plus 1 equal to the 0. So we get 3C squared minus 2C minus 1 equal to the 0. You have to solve this equation. You got to be careful. This is where you make a mistake usually, okay, when you want to solve this equation. First thing to do, you have to move it to the left, remember. You move it to the left, okay, always. Then decide to, if you are good in factoring, you can factor this one right away. The sum of the coefficients are 0. You see 3 minus 2 minus 1 is 0. One of the solution is 1. The other solution is C over A, -1/3, if you know this shortcut. If you don't know it, you factor it. You factor it into the C minus 1 times the 3C plus 1. You go to the 0. Or use quadratic formula. So you have various choices. Make sure you are able to do it. I'm going to do it on the other side. But you may have to use quadratic formula again, be prepared. So this is the equation that you want to solve. 3c squared minus 2c minus 1 equal to the 0. You can factor it if you like. That gives c minus 1 times 3c plus 1 equal to the 0. Otherwise, use quadratic formula. So the first factor give you c minus 1 equal to the 0. That give you c equal to 1. One solution. 3c plus 1 equal to the 0. That give you 3c equal to the negative 1. So c would be negative 1/3. Okay, so you have two solutions, but remember your interval is a negative 1 and 1. So only this one is inside. It's okay to have both of them, but since the theorem that we have, you see a kind of checking. The checking is that the c equal to the negative 1/3 is inside negative 1 and 1. You see, 1 is the end point, if you like. We don't usually take that one. Is inside negative 1 and 1, so you have one solution. Even both of them are going to be the case, but because of the condition of your theorem, we just pick the point which are going to be inside, and that's it. That gives you the result. Any question? So it's not a difficult. You see the conclusion of everything I did so far is just on this problem. But I wanted to understand it. That's why we spend time on it, because that's a great theorem, really. We cannot ignore it. But we give you one question only on this one. Okay, that's it. So let's have a break. If we come back, I'll give you one more example of the mean value theorem to see when this condition would fail, if you like. And then we have the first, we go to the 3.3. There are some application of the mean value theorem. We talk about it later when we need it, when we get to the integration. So we go on to the 3.3 and we try to get the first derivative test as well today. So one question on the mean value theorem. It's a 9:17, okay? So let's come back at 9:30. And then we try to give you the first derivative test. It's very easy, and you get one question on the test. Okay, see you then. Okay, we're going to continue. Any question? So when you check the mean value theorem, especially the problem in your book, you have to check the condition. You see, for example, you have a couple of them in your book that it may not satisfy. I'll just give you one of them so that you know this is it. But on the test, we give you one that would like you to be able to go through it. So this is the kind from your book. I ask you to determine if the mean value theorem, MVT, it can be applied. Okay, can be applied to this function, to the function. Just pick one of them, and there's going to be one in your practice one that we talk about it tomorrow. But the one that you're going to see, it's going to be straightforward. It's going to be x over 3x over x minus 2, and the given interval is 1 and 3. This means a rational function or the radical function. You got to be careful. It may not go through those interval. See, we have to check the condition first. So the solution is going to be, you check the first condition. The first condition is continuity. It's a rational function. So where the rational function is continuous. Remember the rational function? For the rational function, you have to worry about the denominator. Denominator is x minus 2. So this function is not continuous where the denominator is 0. So you have to check to see for which value of x the denominator would be 0. Any suggestion? For which value of x this denominator would be 0? Number 2, very good. Yeah, when x is equal to 2, the denominator would be 0. But you check 2 is inside this interval. So this means this function won't have the first condition of the mean value theorem. Because the graph, the function must be, remember, it must be continuous for every number inside the interval. So you lose the first condition and then you cannot use it. Okay, this is the type you see in your book. So this is how you explain it. You say that f is not continuous. F is not continuous when when x is equal to 2. And you explain that and x equal to 2 is inside this interval. See, that's it. So this means f is not continuous. F is not continuous. If not continuous on the closed interval of 1 and 3, so mean value theorem cannot be applied. So this is the type that you see in your book. I mean, if this interval was something like 3 and 5, you'll be able to do it because in case of the 3 and 3-5 interval of a 3-5, 2 is outside that interval. But since it's inside, you can't do it because there is a hole inside your interval, and mean value theorem cannot be applied. Okay, so when you go through your problems in your assignments, you will see this type of things. So be aware of that. And when it's a radical function or it's going to be rational functions, there is a possibility that you may not be able to do it. But our examples are mostly polynomials and they are nice. Any question? So that will wrap up the theorem, mean value theorem. Okay, so just read through it. Just make sure you are able to do it. The proof is just for your information. The idea of the rules theorem, the same thing, but it's nice to know, to understand the concept. But make sure you know the mean value theorem. And you will see in a minute that I'm going to apply it. Okay, so we are done with the 3.2. We get to the 3.3, which is a very dense section. And we try to finish it by tomorrow. And this is where we give you the test. So you say, remember our target is how we're going to find the relative maximum and relative minimum. So we did the mean value theorem, so we get the nice, and you saw that the maximum and the minimum that I use, and they were not absolute. The point C was inside those intervals. So that will tell you that these points are available and they have some nice properties like the one that I applied in the mean value theorem. So the question is, how are we going to locate them generally? Okay, so we're going to talk about the absolute max, absolute mean. Make sure you know the difference. But in this section, which is going to be 3.3, we start talking about, okay, so we start talking about the locating relative maximum and the relative minimum. Okay, let's make sure I give you the correct section number. Yes, it's a 3.3. 3.3. So let's locating, finding, locating a relative, okay, relative extrema or local. In some books they say local. It's the same thing. Relative extrema means relative maximum and the relative minimum. Now, the result, there is going to be a theorem. We refer to it as a, okay, we refer to it as a first derivative test. So what would be that theorem? I give an idea, then we start working on it. See, consider this graph over here. You see at this point, you get a minimum. Okay, it's going to be a minimum. So we want to find, you know, that the position or the possibility going to be critical points. Or we find the critical values and we find out that there is a possibility that you may get a maximum and the minimum. But the question is, which one is it? How are we going to describe the minimum here? In order to describe it, we're just using the idea of a tangent line. You see, in order to get the one way to look at it is you get to the minimum, the graph going down here and then going up here. So if you go down, then up, that's a minimum. But if you do the other way around, you see that we do the maximum. So for the maximum, you go up and then you go down. You see up, down, if it was a straight line, going down means the slope is negative. Going up means the slope is positive. So if you want to have a different, similar version, the slope in calculus is derivative. So over here, derivative must be negative. And over here, derivative must be positive. F prime. And to describe the maximum, up first, down next. You see? That gives us a nice result to check. So this means you find the critical values and you check the sign of the prime around it. If before is negative, after positive, it's a minimum. Before is positive, then negative, that gives you maximum. Okay, this result is going to be called the first derivative test. First derivative test. We refer to it as a first derivative test. That's it. We are going to give you the actual statement and just do it. And before doing that first derivative test is going up and going down. We have a special expression for it. When the function is up, 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 we say the function is increasing. When it's down, 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 we say the function is decreasing. So we're using this idea of the increasing, decreasing. So we have to define these and get the final result. And then we're done. Okay. So what's going to be the official version of what we talk about it? Definition. Definition is going to be, we have a function. I'm going to define this going up, going down, put them together. And at the end of the day, we get the theorem and then we're done. Okay, so let's get definition. Suppose you have this type of definition in your college algebra pre-calculus course, but we are going to connect it to the derivative. Suppose a function f is defined Okay, suppose it's defined on an interval domain. On an interval, we call it I. It's not going to be a closed interval. First, I want to define increasing function, up, up, up. F is increasing. F is increasing on I if we go from left to right in the domain of the function, the value of function go up, up, up. So if when x1 is less than x2, you pick two numbers from the left to right, that would implies that f of x1 is also less than f of x2. You see, this is going to be true for all x1 and x2 in I. Basically, from left to right, this direction is the same, less, less. If it's going to be greater than, would be greater. In some books, they go with the less than equal to, okay? It's not a big deal, but you have two different names for it. If you put the equality, this is the increasing that we go, we can go with this one. If you don't put the inequality, say a strictly inequality, a strictly increasing, but we just stay with one case. Okay, and we call it increasing. So this is the case for the increasing function. We do the other way around. So this is up, 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 now down, down, down. F is decreasing. Okay, decreasing on I interval. If we go from left to right, you pick two numbers, x1 less than x2. So the direction of the value of the function would be the other way around. It's going to be greater than or equal to the f of x2. You see over here, x1 is less than x2, but f of x1 is greater than f of x2. If this is going to be the case, we say the function is going to be decreasing. Okay, so increasing, decreasing function, as you did it in your calculus course. Okay, the example, we just give you some graph, then we give you the theorem to prove it. The standard one is going to be example number one. Number one, you can consider this graph. Okay, as you can see, up, up, up. It's increasing function. You can pick any 2 points you like. You see, if you pick the point like, if this is going to be your x1, and this is going to be your x2. As you can see, this is going to be your f of x1, and this is going to be your f of x2. So as you can see from left to right, so x1 is less than x2, but the value of the function is the other way. It's going to be the same thing. So go from left to right, up, up, up. So f is increasing. F is increasing. Up, up, up. Any question? The other way around? Look at this one. Another graph. This time you're going down. See from left to right, your graph going down, down. So in this case, if you pick 2 points, if this is going to be your x1, this is your x1, and this is going to be your f of x1. But if you get another point, this is x2, and this is going to be your f of x2. As you can see, as you move on from left to right, the direction of the value of the function or direction of the function is going to be different. F of x1 this time is going to be greater than f of x2. So it's a done. So f is going to be, f is decreasing. Okay, increasing, decreasing. You get these numbers. Or sometimes you make the function go increasing or may go decreasing. Any question? Now, in the previous course in algebra, you didn't have calculus. So in order to prove this, you consider the difference between these two numbers. You say f of x1 minus f of x2, and you try to see if this difference is positive or negative. It's the way you did it in algebra. But in calculus, of course, we are going to connect them to the slope derivative of the function. How are we going to connect them? We are going to use, of course, okay, the derivative. You see, as I did over here. So if you consider it with the slope, up means derivative is positive. Down means derivative is negative. So we check the sign of the derivative of the function. If the derivative is positive on one interval, positive means up, so the function is increasing. If it's going to be negative, it's going to be decreasing. Okay, so we give you the great theorem. And of course, how we're going to prove that theorem? Mean value theorem. You see, anything. One of the famous application of the mean value theorem is this so-called concavity, we call it the test for the function to be monotonic, increasing or decreasing. But easy test theorem. This is the foundation of that would give us the first derivative test. So what is this? If f is differentiable, okay, differentiable function is going to be if f is a differentiable function on an interval domain I. Okay, then this is what will happen. Then the conclusion are going to be the following. And the first one, just put this then down. The first one, if the derivative is positive, you see, if f is positive, if f prime of x is positive, of course, for all x in this interval I, positive means up, then f is increasing. F is increasing on I. That's it. That's the first condition. The second one, if f prime of x is negative, it's going down. Okay, negative for all x in I, then f is decreasing. So it's not surprising because it's like the slope. Of course, there is a third possibility. What is the third possibility for f prime? Positive, negative. What's the third case? Any suggestion?
Equals 0 or does
Excellent.
not exist.
Yeah, equals 0. Since they give you differentiability, it does exist. Okay, if f prime of x equal to the 0, that's interesting. For all x in I, then any suggestion? If
F,
the
F is decreasing.
no. If just think about it. Can you think about a function whose derivative is 0? Can you think about a function whose derivative is 0? You know the derivative is the slope. When the slope is
Horizontal line.
excellent, horizontal line or a constant function. Yes, excellent. Yeah, you know that when derivative is 0, this means the slope is 0. When the slope is 0, if it's going to be the line, it's going to be horizontal line. But in general, if the derivative of a function is 0, that function is a constant function. Okay, a constant function. So this is going to be used quite a lot later on. Then f is a constant function. F is a constant function. Constant function. So it's like, it's going to be a straight line. Yes, that's a straight line. In this, it's going to be a horizontal line in that case. You see, this is going to be 3 possibilities that we can have. Now, how are we going to prove it? Mean value theorem. Great theorem. Okay, to prove this using the mean value theorem. And those people that I told you that they are very jealous about mean value theorem, they prove this theorem without mean value theorem, but they prove are very interesting. But you have to be a math major and you already done 3 years of mathematics to be able to understand it. That's why we are not going to do it. So I can prove all of them using the mean value theorem. I do the last one because they are very similar to prove it. Okay, so the last one is quite interesting and we are going to use it in the second part of the course when we get to the integration. So I do the third. All of them are the same really. For all of them you have to pick 2 x1 and x2. You see, suppose x1 and x2 are in I with the condition that for this third case, you say the condition that they are not equal to each other. For this case, increasing one on the decreasing one, I assume that x1 is less than x2. Okay, and you can assume this all the time, you see. So for example, let x1 to be less than x2. Because if you pick 2 numbers, okay, if you pick 2 numbers, then one of them is less than the other one. In all the 3 cases, that's your starting point. Then what you are going to do is, you see, then your function is differentiable. When a function is differentiable, it's continuous. So you can say that then, you see, f is continuous on a closed interval of x1 and x2, and is differentiable because it's given to you. Differentiable on open interval of x1 and x2. You see, for all the 3 cases, you can use the mean value theorem. Let's see, MVT can be applied. Can be applied. Which is, you see MVT, f of x2 minus f of x1 is equal to the f prime of c times x2 minus x1. So it depends which of these cases are going to use. See, if it is going to be a case 1, f prime is positive. So f prime positive, this is also positive. This would be positive. Let me write it. I can give you all the proofs. Now that I write it down, you see, this is, or the third one is very easy really. The third one, let's stay with the third one. You see in the third one, f prime of c is 0. So we say that bet f prime of z is 0. So this means what? This means f of x2 minus f of x1 is equal to the 0. And that will tell you that f of x2 is equal to the f of x1. So this simply means f is a constant function. F is constant. Because you know that if you have f of x equal to 5, then f of 10 would be 5. F of 10,000 would be 5. F of radical 2 would be 5. So what we did, we picked two numbers and we proved that the value of function at those two numbers are always the same. So in that case, your function is going to be a constant function. Done. If you are going to be in the first case, you say f prime of c is positive. When it's going to be positive, this difference would be positive. So you move one of them to the other side, you compare them together. F of x2 would be bigger than f of x1. If you want to use the second part, we say it's negative. So in all cases, you're just using the mean value theorem and you prove it. It's a great theorem. Without mean value theorem, you can't do it. So that would be very nice application. But this last one is interesting. We are going to use it later on. Okay, if the derivative of the function is 0, that function must be a constant function. Any question? Now we can use it to get the mean value, to get the first derivative test. Okay, so what is going to be the first? That the price. Okay, we do this one, but the price is going to be the first derivative test. So this is it. 2 questions on the first derivative test. Or maybe 1, okay, but there are 2 different cases. What is first derivative test? It's a great test, but we have another one, the second one. Most of the people prepare the second one. We have to know this one too. What's the first derivative test? Remember those up, down that I talk about it. I'm going to make it official. Suppose f is, again, is a given function. You see, a function is given to you. You already got your critical value, and you want to know whether at that critical value, you are going to have a maximum or a minimum. So that's the application of this. So suppose f is a given function, and the number c is a critical value or number. Critical value of f. So you have this. You don't know whether it's a maximum or the minimum. So this is how we're going to use the Ferris test. Now I'm going to describe minimum first. So minimum first, I go down. You see, this is minimum. Minimum. In order to get the minimum, the graph go down means decreasing. So f prime must be negative. And then up. F prime must be positive. Okay, so this is going to be the condition that we are going to have over here. Okay, so what is going to be the case to make sure I haven't lost there? Okay, that's it. So I'm describing the minimum for you. What's the minimum? If f prime of x is negative before c, for x less than c, and f prime of x is positive after c. Okay, for x greater than c. If this is going to be the case, then f of c is a relative or local. Relative minimum value of f, or just relative minimum, you know that. Okay, so that's the case for the relative minimum. Any question? So we need a chart, or we check. You have to check 2 numbers. One before C, one after C, to show us that this is down, up. That's minimum. Question? Let's describe the maximum. Maximum, up first, then down. That's a maximum. Maximum. Up means f prime is positive. Down means f prime is negative. So before C, positive after. So if f prime of x is positive before C, or x less than C, and f prime of x is negative for x after C, then f of C is a relative. Okay, it's going to be relative maximum. And we done. Nice test. It's a nice test. It's a double bonus problem, because in this problem, you are going to check where the function is going to be increasing, decreasing, and then you give us the maximum or a minimum. One on this test and one on the final. Because one derivative, one first derivative test on the final too. Okay. So you have to find the critical value first. And I usually go with the chart. I draw a table and identify the sign of the f prime to the right, to the left of the C, and then I do it. Some people, they just drop numbers in it. So let's see how I'm going to do it. I prefer this method that I go to, right? Just make sure to give us enough information, okay? So that's it. You have, I think, a couple of them in your practice one. We give you one on this test and one on the final. Okay, are you ready? Let's try to see if you see get a couple of them. There you are. Determine. Okay, determine the intervals. This is the way they express the problem, and then you find out that using first derivative test. Determine the intervals where the function would be given. This is the function f of x. It can be a polynomial at this level, or it can be a trigonometric one. X cubed minus 3x plus 1. When we go to the final, it may be natural log or it will be exponential function. This is the way we check it. Okay, determine intervals where the function is increasing, okay, or decreasing. So they ask you for those intervals. You have to give us those intervals. Okay, decreasing. And then they ask, find all relative. Okay, relative extrema means you have to identify for us which is the relative minimum and which is the relative maximum. There you are. Are you ready? 2 steps problem. The first one, that 50% that we talked about before. You have to find critical numbers first. The second step, you need a chart for the f prime. Check to see what is this situation going to be. Okay, so do it step by step. Solution, you need the domain to start with. It's a polynomial, so the domain would be R. So you check the derivative to find the critical values. F prime would be 3x squared minus 3. Okay, you let it equal to the 0. In this case, it's a 3x squared minus 3 equal to the 0. You solve this equation, 3x squared equal to the 3, x squared equal to the 1. Okay, and you get x equal to the positive negative 1. So you have two critical values, negative 1 and 1. This is the step 1. Any question? There is no other source to find the critical value. Remember, we have two sources, horizontal tangent line and the vertical one. The vertical one comes when we get to the radical function. So in this case, we are done. We have find all the critical values. Okay, that's a step 1. Question? Step 2. They are the candidates. Drop them back into the function to find the values, because the values are the one they are interested in. Okay, so step 2, evaluation of the function at the critical points. F of -1 into the function, -1 cubed minus 3 times -1 plus 1. It's going to be -1 plus 3 plus 1, which is equal to 3. So f of -1 equal to 3 is one of the candidate for the maximum or the minimum. That's f of -1. You do the same thing for the second number. So we find f of 1. F of 1, 1 minus 3 plus 1. So that gives it 2 minus 3. Okay, which is going to be -1. So the second candidate is f of 1 equal to -1. That's it. That complete the step 1 or the step 2. Now, next f prime, you have to check the sign of the f prime. You have to check the numbers around this. I go with the chart. We prefer this one. You are going to provide a chart for us. Okay, this is going to be the chart. The chart would start with the x, then start with the f prime of x, and the function f of x. So on the pairs part, you put the domain, which is the -infinity to +infinity. That's a domain. You put in the critical values. You have a -1 and 1. It's a -1 and 1. Any question? So on the number line, from the smaller number to the bigger one. Then you identify that these are critical values. So the f prime is 0 at -1. And f prime 0 is +1. You see? You partition f prime into 3 parts. 1, 2, 3. So you have to find the sign of the f prime in these 3 cases. F of -1, of course, is we have this one. It's equal to 3. And f of +1 is equal to the -1. Now, there are different ways to describe the sign of the f prime. If it's going to be a quadratic expression, it's easy. According to what you have learned in algebra, if it's a quadratic expression with 2 solutions, between 2 solutions, the sign of the expression is opposite sign of the x squared. Between 2 solutions, the sign is opposite sign of the x squared. Otherwise, it's the same signs. Opposite, the same signs of the x squared. So the sign of the x squared is positive, so opposite would be negative. Outside, positive, positive. That's the way we do for the quadratic, quickly. Okay. Now, if it is not going to be quadratic, as you did it in algebra, in each part, 1, 2, 3, you have to pick 3 numbers. We call it testing numbers. You pick a number, for example, between -1 and 1, we can pick 0. If you put the 0 into f prime, that gives you 0 minus 3, which is 3. -3 is negative. So in this interval, we pick another number. So we pick the numbers in the trigonometric one, in future exponential one, the numbers. But for the quadratic or the polynomials, it's easy. Okay, 2 solutions, between the solutions, opposite, otherwise the same. If you have no solution for the quadratic and 1 solution, the sign is always sign of the x squared. This is from algebra. Otherwise, pick 3 numbers. We don't need to pick numbers for this. Okay, any question? Now the conclusion. The conclusion, f prime positive, remember, positive means increasing up. Negative means decreasing down. Positive means increasing up. There you are. So the function is increasing between the interval of -infinity, -1, and 1 and +infinity. It's decreasing between -1 and 1. If you give us the chart, you don't need to explain it. We understand it. Now, max mean, up, down, maximum. Down, up, minimum. You see, it's done. That's the best way to express it, okay? But some people don't like this. they give me different interpretation, but I'll be happy if you can get it right. But you don't have to explain this one if you write it down in this form. But otherwise, you have to explain when you get your conclusion. So the explanation is that if you want to do different method, but I prefer this one. But the conclusion is f of -3 equal to the -1 equal to 3 is a relative. Okay, it's a relative maximum. Then f of 1 equal to the -1 is a relative, okay, relative minimum. Then the interval f is increasing. F is increasing on these two interval, is increasing on the interval of negative infinity to -1, negative and -1, and then 1 and positive infinity. That's where it's going to be increasing, and it's going to be decreasing. F is decreasing. Decreasing where? On interval of -1 and 1. Okay, the chart as I did it, otherwise you just give us this explanation and be happy. Okay, to be able, because you have to apply the first derivative test, and they ask for the interval where the function can be increasing, decreasing, and of course there you get a maximum or a minimum. But that chart would be useful, and you can do that one as well. Okay, any question? That's case one with the at the moment with the polynomial type. We don't have the natural log and the exponential function, but we give you one trigonometric one of those 6 questions that we talked about before. So we'll get one of them to finish it question. So that's conclusion of today of this section. Either this one or a trigonometric one. So let's check the famous trigonometric on one of those. You need the unit chart. Of course, we give you the unit chart. Okay, so what's going to be the example of this form? Example. Same thing. We wanted to determine, determine the intervals where the function one of those trigonometric one. Let's pick this one. F of x equal to the, how about x minus 2 cosine x when x is between 0 and 2 pi. Okay, this is going to be the case where this function is increasing or decreasing. Okay, and of course they ask for you to find the relative max. Find all relative extrema of the function. Okay, this is the only other possibility that we have so far. You already done everything we need ready. We put them together now. Okay, are you ready? Remind yourself that the domain for this problem is going to be closed interval of 0 and 2 pi. The first part, you did it on the quiz and the test. You differentiate f prime carefully. 1 minus 2 times. The derivative of a cosine is a negative sign. So negative, positive. Make sure don't miss it. 2 sine x. That's f prime. Highlight it. Let it equal to the 0. Then solve this equation carefully. 1, 2 sine x equal to the 0. And you move the 2 sine x, move the 1 to the other side. So we get the sine x equal to the -half. Go table and find it. Unit chart. This is it. And this is going to be the sign. Okay, sign is negative. So where are you? You're going to be either here or you're going to be here. Okay, remember this is cosine, this is going to be sine. So 1/2 is a sine of the 30 degrees. Okay, this is sine of the 30 degrees. This part is pi 6, but this is going to be 210. You're gonna know, you're gonna have it in the table. 210, which is 7 pi 6. And this must be 360 minus 30, 11 by 6, 11 by 6. So x equal to the 7 by 6 and the 11 by 6 are going to be your critical values. Make sure you get it right, because some people they miss this one on the test. You have your unit circle chart and double check it. Any question? So two places that they miss, usually this is it. This is the derivative of a cosine is a negative sign. So negative would be positive. So you should have 2 sine x here. Then you want to solve 1 plus 2 sine equal to 0. Of course, that gives a negative 1 here. So the sign is negative. When the sign is negative, you are going to be either in the third quadrant or the fourth. On the third one is 210 from your table. Okay, and on the fourth, you get 330s. It's going to be 11 by 6. Okay, question? Next, you have to drop them back into the function to find the candidate. Okay, there you are. Carefully drop it to the function. Some people, they miss this part. Remember, it's a maximum value and the minimum value. So you have to find the values. You go to the function substitute, that gives us 7 by 6. 7 by 6 minus 2 cosine of 7 by 6. So it's going to be 7 by 6. Okay, minus 2 times cosine. Cosine of the 7 by 6, the cosine is negative, is a radical, is a minus radical 3/2. Again, you have it in your chart. You can easily find it. So 2 and 2 will cancel out. So that gives you 7 by 6 plus radical 3. We don't accept this number as is. You have to use your calculator and estimate it on the test. Remember, we don't expect it. So pi is 3.14. Okay, so it's going to be 3.14. This is the way I do it. You can check it with your calculator too. So it's going to be divided by 6. Then I will add it to the, that's the radical 3 to 1.7 almost. So I have 2.066. Just check it with your calculator. We should get the same one. 2.606. I call it 2.07. So that's going to be the first one that I have. Okay, so f of 7 by 6. Check it to be, because you want to compare, so you need them. So we don't accept, you say 7 by 6 plus radical 3. Doesn't make sense. Okay, any question? Check your calculator, make sure you get the same number. We have one more, 11 by 6. F of 11 by 6. Go ahead in the function, 11 by 6. And the function, -2 cosine minus 2 cosine of 11 by 6. So it's going to be 11 by 6 minus 2. 11 by 6 is here, cosine is positive. So it's a times a radical 2 over 2. So when you simplify the 2 and the 2, so that gives you 11 by 6, 11 by 6 minus radical 3. Again, use your calculator to get it. It's 11 times 3.14. Then I divide it by 6. Divided by 6, then I add minus root 3, it's almost 1.7. I got 4.0. Okay, I have 4.05 or 5.6. I call it 6. So I got, again, check your calculator. Make sure you get the same number. 11 by 6. I got this one is almost 4.06. 4.006. So these are the candidates for the maximum and the minimum. Any question? We need the chart. Find out which one is going to be the maximum and the minimum. This is going to be your chart. X, f prime of x, and the f of x. The domain this time is 0 and 2 pi. 0, 2 pi. Typical numbers that you have to check are 7 pi 6, 7 pi 6, 11 pi 6. F prime is 0 at 2 places. At the 7 pi 6, we get 2.07, 2.07. At 11 by 6, we get 4.06. So F prime partition 3 parts, 1, 2, 3. You have to identify the sign of the F prime. There are different ways to do it. You can check some numbers in the F prime, or the other way to do it is, you see, find the F of 0 and F of 2 pi and compare these values together. That would be easier. Okay, option is checking the numbers in the F prime, or for a trigonometric one, this method always working. Okay, so what I do, I find f of 0 as well into the function, which is easy. You see f of 0, that gives 0 minus 2 cosine of the 0, 0 minus 2 cosine of the 0. Cosine of the 0 is 1. So that gives me 0 minus 2, which is a negative 2. So I put the negative 2 here. And I find f of 2 pi. F of 2 pi would be to the function 2 pi minus, okay, 2 pi minus 2 cosine of the pi, cosine of the 2 pi. Cosine of the 2 pi is 1. Okay, because the cosine of the 0 is 1. This is going to be the same thing. Okay, so that gives you 2 pi minus 2 again in this case. So that gives you now, it's going to be 628 minus 2, which is going to be 428. So that gives you 4.28. So that's easier, if you like it. So I can compare these numbers now for the case of the trigonometry. From the negative to positive is going to be up. So this is positive, and this is going to be, so this is up. There must be something that I missed number over here, because at this point, this must goes down. I have to check this one. Okay, this must goes down, and then I should get up here. So what would happen to this one? That did we miss anything over here?
On the 7 pi over 6 plus square root 3, I got a different value.
Very good. Excellent. What's the number? What's your number here?
It was around 5, I believe, but it could be wrong.
Yes, you are right. It must be 5. Let's check it again. Because I know that this must go down. So let's check it again. 7 pi, it was 7 pi 6, yes? 7 times 3.14. Okay, then I have to divide it by 6. Divide by 6. Then plus. Okay, then plus 1.7. 1.7. You are right. Excellent. 536. 536. 536. Excellent. So that would be 536. Now that makes sense. Okay, so because when you work these numbers. Yeah, so that was wrong. Check it with your calculator. 536. So from so that's going to be the case. So from -2 to the 536, it's up. So from 536 to the 4.06, it's going to be down. So this is going to be negative, and then up, which is positive. That makes sense now. If you check it with your calculator, graph it, You will see this. Okay, so this is it. We get a maximum here, and we get a minimum here. And okay, 11 by 6. And